column chromatography in order to separate proteins based on differences in the protein's properties and how that causes them to interact differently with the properties of the resin, so the little beads filling these columns. Different proteins are going to interact differently and thus come out or elute from the column at different times. And we can see when they come out because we have a UV monitor that's going to monitor the absorption of the light that is caused by the proteins coming out or eluting. And so we get these peaks that tell us when the protein comes out. If we're trying to separate proteins, we want those peaks to be far apart from one another and not overlapping. We say that's good resolution when we have these peaks that are well separated from one another, they're not overlapping, that's good resolution, and we can even go and isolate the different peaks to isolate the different proteins. But all that depends on having good resolution. I like to think of it a bit like people on a bus and whether their legs are getting tangled up. And their legs getting tangled up would be poor resolution. And whether their legs are getting tangled up is going to depend on how close together the seats are, as well as whether they're kind of like spreading out their legs. So, man spreaders, we're talking about you. That would be poor efficiency, whereas selectivity is going to be how far apart the seats are. So, how far apart the seats are is going to be your selectivity, and then the man spreadedness is going to be your efficiency. And so selectivity is how far apart the centers of the peaks are, then efficiency is how broad the peaks are. And so it's kind of the combination of the two that determines whether or not the peaks are overlapping, whether or not the people's feet are tangling up with one another. So selectivity and efficiency. And where does this come from? Well, this comes from the interactions of the molecules as they're moving through and interacting with the beads. That's going to give you the selectivity and going to tell you, like, is the resin selective for this molecule over the other? Can it differentiate between those two based on the properties of the resin, so of the little beads, and of the ligands, so the groups that are attached to the beads, as the molecule's moving through under certain buffer conditions? That's going to determine your selectivity. The efficiency is going to not depend as much on the molecule interacting with the beads themselves, like the surface of them, but actually moving around them. And so if you think about these beads are circular, and you have this column full of these circular beads, so there's going to be some air gaps in between them. The bigger those kind of gaps, or not air gaps in this case, they're going to be filled with solvent. There's hopefully not air in there. And so that's going to be kind of places where your molecule can diffuse around. And so it can kind of move back and forth. And when it's moving back and forth and diffusing, you're getting zone separation. Basically, what's going to happen is your peak is going to broaden. If you have really big gaps, then it's going to broaden more. And so you could have really big gaps if your column is packed badly, or if the beads are bigger. And so if you have these bigger beads, think of like beach balls, there's more space in between beach balls in the column than there would be between like golf balls in the column or ping pong balls. And so the more space there is in between there, the more room there is for the molecules to wander around, and then you're going to have a broader peak. And when you've got a broader peak, then you've got poor efficiency. So efficiency, what you want is you've got nice, crisp, narrow peaks that are symmetrical. If you have something like this, that'd be non-efficient. And if you have something like this, that would be efficient. And again, that comes down mainly to the size of the beads. And so if you have these smaller beads, you're going to get better efficiency, you're going to get sharper peaks, but you're going to be building up pressure, and so you're going to have to run the flow rate slower. And so that is why you might choose, and like, okay, I'll take the bigger beads because I can use a faster flow rate. And so you'll often see that you can buy these columns in these different formats with the small beads, which is great for having high efficiency, getting those sharp peaks. And then you'll have the kind of bigger beads, which is good for like fast flow. And again, that's the efficiency. The selectivity is going to come down to the properties, basically, mostly of the surface of the beads, of the ligands on the beads, say, as well as to the kind of the buffer conditions, because the buffer conditions are going to impact how the molecules are interacting with the properties of the resin And so the properties of the resin I'm talking about here are kind of like the differences between what's on the surface of the beads as opposed to the differences in the size of the beads. So the size of the beads is largely going to efficiency, and the properties of the beads themselves is largely going to go, or at least the things attached to the beads is going to go towards the selectivity. And so different beads have different properties, and so you might need to try different columns in order to find the beads that are best for resolving the proteins that you want to separate. And so this is actually like a selection kit for a technique called HIC, Hydrophobic Interaction Chromatography. And so basically this uses these beads that have nonpolar groups or hydrophobic groups on the surface that are then going to interact with hydrophobic or nonpolar groups on the surface of proteins. And because different proteins have different things on their surface, they're going to interact differently. And you can take advantage of salt concentrations to take advantage of the different properties and elute them differently and stuff. But there's different proteins will also interact differently with different ligands on these resin. And so there's things like butyl and phenyl groups. You can get different types of the ligands that are attached to these. And those would each have a different interaction profile with the molecule that you're looking at, or the molecules. Because typically you're trying to resolve multiple molecules from one another, basically. And so you want something that's able to well differentiate between the two of them, and so you want something that's going to be selective. And so the selectivity, remember, that's how far apart the peaks are. But then you need to think about, okay, well now I found this ligand that works well in being selective, but what if I'm getting these peak broadening? That'd be bad efficiency, which can make it so that even though they're farther apart in their centers, they're actually overlapping in their peaks. And so then you might go from, say, one of the bigger bead sizes to one of the smaller bead sizes. And you might scale things up after you find the right conditions with your sample kit or your sampler kit type of thing. But then you could also say that use the same thing but change the conditions of your buffer in order to try to get better selectivity with the same column. And so there's a lot of different optimization and that sort of thing that you can do in order to get good resolution with a technique like HIC. Then with any technique for the resolution, you want to make sure too that you're not overloading the column. Basically, if you overload it, you load too much protein, your peaks are going to be broader. So the more protein you're loading, the kind of broader your peaks are going to be inherently. And so you need to keep that in mind. And you also want to keep in mind that if you load too much, then you're going to saturate your detector and you kind of all you see is like, that's not what you want. What you do want, nice sharp symmetrical peaks, good efficiency. And the peak centers being separated, good selectivity. The combination of those two, so those bus pleats far apart and you're not man-spreading, that's going to give you that good resolution. And so resolution is basically whether their peaks are overlapping. And so there's actually a mathematical formula that we can use for this to really describe resolution. So resolution, like mathematically in chromatography, is going to be the distance between the peaks divided by the average width of the base of the peak. And you need that value to be above 1.5 to have separation of the peaks at their bases. And so that's resolution mathematically, but typically we just think about, are those peaks overlapping? And if those peaks are overlapping, then it's going to be hard to go and isolate one of the proteins from the other protein. And so we want good resolution, we want good separation, which comes down to the selectivity and the efficiency. Overall, that's going to give us the resolution or the not resolution.